Um, Hi, Ben here. So I'm going to be talking about the a paper review. This paper proposes a network called, which they call CGBNet, and it's a deep learning framework for compost classification. So the problem they're looking at here is climate change due to landfills, and they are particularly focusing on the United States. Research has shown that wastes emit a significant amount of uh, greenhouse emissions. But this can be mitigated by controlling waste buildup using methods including composting. So composting is simply the process of making a mixture of decayed organic matter. And the key aspect here is distinguishing between uh, green and brown compost, which is typically done when composting. Some of the gaps they identified in their literature review was the fact that a number of datasets that are out there currently are focused on waste categories rather than compost categories. And there's also uneven data distribution, which limits the practical applicability. Furthermore, research on composting that proposes technology-enabled solutions usually focuses on maintaining existing compost piles rather than creating new ones or helping create new ones. And lastly, the architectures that are proposed are predominantly complex and cannot accommodate instances where you have smaller data sets. So for their data set, they propose two labeling structures where you have a superclass and then a subclass. So for every compost item, so for both classes of compost, that is green and brown compost, you can have a number of categories. For example, apple cores, banana peels, carrot peelings for greenhouse, and these examples for brown compost as well. So they suggested these two strategies of labeling. And then so they did get this data from the internet, and they had approximately 100 images for each subclass, which formed a total of 1,960 images. So they went ahead and split this data into 80% and 20% to accommodate the train and validation partitions. So furthermore, they scraped more images to generate a test set. So since their data set size was limited, they employed the Keras Data Augmentation API to diversify their data set using attributes such as rotation and vertical flipping, but they do not explicitly specify the range of values they use for these specific augmentations. So for classification, they explored a number of architectures, predominantly state-of-the-art architectures that have been proposed over the years. So we see Exception, EfficientNet B7, ResNet 50, Inception V3. And exceptionally, they came up with a modified exception model, and they also came up with their base with a model that they called CGBNet, which uses DenseNet for its convolution part. So for all models, they were typically getting a CNN architecture, and then they add a dense layer, two dense layers followed with dropouts, and a final dense layer, which they link to an output layer. So the output depended on what kind of classification they were doing. So for the superclass where you have two classes, they used sigmoid, which is for binary classification. And then for the subclasses where you have various classes, they use softmax. So for their modified exception model, they pretty much took a subset of layers from the original exception. So on the left hand side, I have the original architecture, and then on the right hand side, I have a summary of their proposed exception. So they essentially take a pair of convolution and ReLU layers, as we can see these two. And then on top of that, they have 4 residual blocks, and each residual block includes two pairs of ReLU on top of a convolution layer, on top of convolution layers, followed by max pooling. And as we can see here, so separable conv, ReLU, and max pooling. So they take like these blocks and make like 4 residues of these, and then finally they add a separable convolution layer with global average pooling to seal their convolution part of the architecture. So for the rest of the modified exception, it is what I've discussed in the previous slide. So their training pipeline essentially, it's something like this. So it depends on what classification they're doing. So if it's superclass classification, they merge the subclasses into these 2 superclasses, and then they take that to the model architecture. So at the output, they have a sigmoid because it's a binary classification. And then for the subclasses, it doesn't differ that much, just that you have multiple classes. And then you take in those subclasses into your architecture, and then at the output, you have a softmax to implement the categorical classification with multiple classes. For the loss function, they use binary cross entropy for the superclass and categorical cross entropy for the subclass. For training from scratch, these were their hyperparameters. So 50 epochs, 32 batch size, and the Adam optimizer with this learning grid. This was common among all architectures. And then for transfer learning, they used weights generated from pre-training with ImageNet, which is a dataset, a computer vision dataset with over 10 million images and 20 labeled classes. So again, these were their hyperparameters for the transfer learning bits. And maybe the only difference is the learning rate is slightly lower, and they use stochastic gradient descent for optimization. But these were their results, which were pretty impressive. You see, they have so they use accuracy, precision, and recall and F1 score metrics to assess their models, but they predominantly focus on the accuracy score. When you see, they have 95% for their CGBNet on the subclass and 93% on the superclass, which is interesting. They also have they also show that their modified exception outperformed all the other architectures for training from scratch. So in conclusion, they do have impressive results, but it's still quite a black box. It is not clear how this model comes to a conclusion that a particular object is green compost or brown compost, especially when it comes to the superclass. So for example, you see the pepper and the egg white, they look quite similar, but this model is able to distinguish these two despite having a high variance, given the fact that there's also other classes that may look very, very different than these. So it's not quite clear how the model comes to this conclusion. So it would be interesting to conduct some explainability study on this model to gain confidence in these results. Thank you.